All right. So let me talk a little bit about a few of these agenda items. Number one, Wellness Wednesday sign up. So if you have notifications turned on for announcements, you may have noticed this weekend I put up an announcement about the Wellness Wednesday activity we're doing this Wednesday. It'll be from 2 to 3:30 p.m. It'll be in the Idea Lab in the physics room. It's only open to my physics students and AP Physics. And it's only open to 12 students because we have to keep our cohorts of 12 or fewer. So on the announcement, there's a link to a Google document. And for some reason, I've tried multiple different settings. And I don't know if it's because I'm doing it through the Oaks platform. Even though you guys are all students with Oaks emails, it still seems to make you ask for permission to join. So I've had a few students that saw the announcement over the weekend and asked for permission to have access to it, and one student that signed up so far. So if you think you might be interested in basically what we'll be doing Wednesday, you'll go through the normal check-in procedure. You'll go through the gym and get your temperature checked, and then you'll come to the physics lab and the Idea Lab. And we'll be doing, I've got a few different labs I'm trying to decide amongst. I'm trying to figure out which ones would best fit in the basically hour and a half time frame we've got, and give you an opportunity to learn about either kinematics or forces. And that's another thing, is we've just finished kinematics and we're just starting forces. So trying to decide, looking through all my labs, and I just having a hard time nailing down which one I want you to work on Wednesday. But basically trying to think of something that would give you a chance to use some of the technology we have for labs and practice doing a little mini lab. It's not for a grade. It's not for any kind of extra bonus credit or anything. It's just for experience. So if you're curious, you'd like to come in and try some of the equipment, like to come in and see the physics room, that's an opportunity. It'll just be this Wednesday, 2 to 3:30. So first 12 that sign up on that Google Doc will be the 12 that are able to come. Once it's filled up with 12, if you do check later, if there's already 12 names, you'll just have to wait for another opportunity if we can have one. There aren't very many more Wellness Wednesdays available, and I've got electrical engineering on, I think, the only one after this one. So it's probably the only one this semester. And assuming we're back on campus next semester, it would be a moot point. So hopefully, if you're able and interested, you can come this Wednesday. The other thing for Unit 4 test, I've graded all the tests for A Day. So for your class, they're graded. I haven't put the grades into Axis yet. I'm still putting them into the spreadsheet and getting the curved scores. So I'll be doing that hopefully later this afternoon. I'd have a few tests to still grade from B Day. I've got all the international ones done. I've got all the A Day done. I got a lot of the B Day done. But so I just need to finish that this afternoon and then get them all put into Axis. I'm going to this time go ahead and put in your curved grade immediately. Normally I put in the original score, and then once you've completed the corrections, then I change it to the curved grade. I'm going to do that backwards this time. I'm going to put in the curved grade, and then as long as you do the corrections, it'll stay that way. If you don't do the corrections, then you'll revert to the uncurved grade. So I think what that'll end up doing is enabling me to not have to change so many. I can just change the very few that don't end up doing the corrections. So now the corrections are due by next Monday night. So you have a week to get the corrections done. I want to get everything done before Thanksgiving break. And so we have kind of a fresh start after the break with all new material and all new tests and such. So the test corrections, you have a week, and there is an announcement, just like there's an announcement on Axis for the Wellness Wednesday sign up, there is an announcement on Axis as well about these test corrections and retakes. And it reminds you when the test corrections are due next Monday night. It also tells you you can do retakes on Thursday or Friday or Monday at 4 o'clock for any of those three options. So this Thursday, this Friday, or next Monday. And so that's all detailed in the announcements. If you miss it here, if your microphone or your speaker went out when I was explaining it or whatever, it's all listed on that announcement. But that is, I want to get everything done for Unit 4 before the break so that we just have a fresh start when we come back. Today, we're going to be taking notes on forces and introducing Newton's laws. And then your assignment for tonight is there's no written assignment, but I want you to do readings number 2 and 3, also from Axis. So hopefully you did reading number 1 that was due today. You're going to see some of the things that were in that reading kind of pop up in our notes today, but I'm going to go over those parts of our notes pretty quickly because I'm assuming you either have read it or will read it. I'm not going to define all of those things as fully because they are in that reading. So if you didn't do it, if you forgot, you'll need to do readings 1, 2, and 3 because I'm only going to be touching on some of those things in the notes. So make sure you're doing that. There is a long-term assignment. If you would like to get an early start on it, you basically have the next 2 weeks to get the Positive Physics Unit 5 Introduction to Forces assessment done. So you'll go to the Positive Physics website. You will use the work section for practice if you choose, but that is purely optional. I would strongly suggest that you do not use the extra practice. I've had a few of my international students especially use the extra practice section, and there's really not much advantage as a student for you to do that. Everything that's in the extra practice is also in the work section. And when you do the extra practice, you can't immediately correct it. You have to finish them all, then justify or finalize before you can correct it. It's more like the assessment, but the problem is I've had a few students who, when they've finalized that extra practice tab, it's locked them out of the assessment. And so then they have to write me and then I have to unlock it for them. It's a bug in the system. I've written to the creators of the website many times. And this weekend, they finally think they narrowed it down that that's the culprit, that it's when a student uses the extra practice and finalizes it, then it sometimes locks him out of the assessment. So my recommendation, just don't use the extra work or extra assignment tab. Or extra practice, I think it's called, extra practice tab. It really gives you no more value than the work section. The work section has videos, you can do corrections immediately. It has more questions to choose from. So I would, if you're going to practice, use the work section. Don't use the extra practice section, is my recommendation. But you have to, what you're graded on is the assessment. And you will get the average between your original score and your corrections score. I'll give you a quick rundown here, but if you forget this detail, these instructions are also in a document on the bulletin board page of Axis. It's Positive Physics Instructions. You can open up that document and be refreshed of all these details. But basically, you can do the work section as much as you want. It's just optional, gives you practice. There's videos, all kinds of stuff. When you do the assessment, you have to click check answers for every single question in order for it to save your work. Okay, so when you're done with a question, click check answers. It will save your work. If it's wrong, you can't immediately correct it. You can only correct it after you've finished the whole assessment. But it won't save your work unless you click check answers. So if you don't click check answers and then you go out of it, when you come back in, your work will not be there any longer. And it'll probably change the numbers that were used in your question. So you have to start over. So to save your work, click check answers. Then after you've done all the questions, I think there's 21 questions. After you've done all 21 questions, then click finalize. So check answers on all 21 and then click finalize when you're done with all 21. Then it allows you to go back in and make corrections. Okay, so all that's explained in the handout. So if you forget, open up the handout on the bulletin board page in the downloads portion, and there's instructions there that lay all that out with pictures and everything. Okay, so if you forget, just use that. But that is due after Thanksgiving break. That I think it's November 30th. November 30th, December 1st kind of combo, the first day we come back after the break. I'm giving you 2 weeks so that if you don't want to work over break, you can just do it this week and get it done. And you've got a full week before break to do that. If you are really busy over this next week, you could still use time over the break to either do all of it or start it or just finish it or whatever. But I'm not actually going to give you much homework this week because I know you're going to be working on that. Mainly the homework I'm going to be giving you is just reading some things that should be pretty quick. And so any extra homework time you have, if you don't want to do it over Thanksgiving break, then just start working on it now. So it's a long-term assignment. Questions about Wellness Wednesday, test corrections, retakes, anything before we jump into today's notes? All right. Hopefully that all makes sense. There are announcements, like I said, about Wellness Wednesday and the test corrections and retakes on the bulletin board page of Access. Read those announcements if you forget the details. There are instructions for positive physics in the downloads of Access on the bulletin board page. You can use those for that. All right, let's jump into the notes. So what causes motion? And maybe even more specifically, what causes change in motion? And that is what this whole unit's going to be about. And my goal, so you understand the big picture, my goal is for us to get through, if you look on Access, you'll see there's a 5A, and then there's a 5B, and then there's a 6. So I've kind of divided up the force unit into 3 sections. And I'm hoping to get through 5A in the 3 sessions we have before Thanksgiving, and then get through 5B in that first week after Thanksgiving, and then do 6 that last week right before Christmas break and exams start. I'm still trying to decide what to do for the exam. There's still some uncertainty about whether students will be allowed to do the exam on campus or not. If we do the exam on campus and the majority of you are going to come, then I have one plan. If we cannot do it on campus, or most of you are unable to come or unwilling to come for safety issues or whatever, then I've got another plan. And so I'm still waiting to hear from the administration which way they're going to go with that. I'm hoping that right after Thanksgiving break, we'll have a clear direction, and I can let you know whether it's going to be a more traditional exam or whether it's going to be something a little less traditional. So one way or another, there will be an evaluation, but I don't know exactly what that's going to look like yet. So I'm still waiting to hear some feedback from the administration. But that's my goal. 5A before Thanksgiving, 5, and probably even a little bit of 5B, and then 5B wrap up the first day or two after Thanksgiving, and then start in Unit 6 to sort of wrap up this first semester before Christmas break. And what causes changes in motion is forces, and forces are the topic for all of those little mini units. They're kind of shorter, and that's why they're divided up, and also trying to wrap it around the break here. So here is one way to define a force. It's not maybe very traditional. If you look up a definition of force online or in your textbook, it probably won't say it this way. But there's something about this definition that I like, and I want to emphasize, because it's something I think a lot of students miss in their understanding of forces. And that is, a force is an interaction between 2 objects or substances. A force can only exist if there are at least 2 objects or substances. One object cannot exert a force on itself. So there has to be 2 objects. Now, sometimes that can be a little unclear or a little bit hard to evaluate or assess, but in reality, there has to be 2 objects for there to be a force in existence. And that actually kind of relates to Newton's third law, which we're going to talk about here in just a few minutes. But another way to say it is that forces come in pairs. So if I push on the wall, the 2 objects are me and the wall, or maybe more specifically, my hand and the wall. And when I push on the wall, I'm applying a force on the wall, and the wall is applying a force back on me. So there has to, for a force to exist, there has to be 2 objects, 2 substances. Can't just be my hand, and it can't just be the wall. It has to be 2. Now, there's many more things we can say about forces, and we will define it a bunch of different ways. But this idea that there has to be 2 objects at least is the first thing I want to cement in your brain. Now let's start digging into Newton's laws. And you might find it strange, but in most books, they start with Newton's first law, then second, then third. They go through them in order. We're starting with the third one. And I picked this up from a few other teachers, physics teachers at conferences I've been to in the summers. And a lot of them found that students tend to do better if you actually start with the third law first. And so I tried that a few times, and it seems to work well. So we are going to begin with the third law. Newton's third law is something you've probably heard, but maybe didn't know it was related to Newton's third law. If you've ever heard the phrase about equal and opposite forces, or for every action there's an equal and opposite reaction, that kind of a phrase, those are things you may have heard that are related to Newton's third law. Now, there's a video that I'm not going to show just for time's sake in our Zoom session, They work okay in a Zoom, but you can always watch the videos on your own if you're interested. So all these videos are posted in the topics 5A, 5B, and Unit 6. So if you want to find these videos, you can go into topics 5A, 5B, or Unit 6 and watch the videos. There's a whole bunch more videos too, but I'm listing some of them in the notes so you can see, oh yeah, there are some videos. The NFL videos are just interesting. It's I think it was maybe National Geographic or someone that they took some NFL footage and they talked about the principles of forces, especially Newton's third law. And there's actually an NFL video for all three laws. So if you want to see those, you can go to those topics for 5A, 5B, and Unit 6 and find these videos and watch them if you're curious. What Newton's third law says is what's on this slide. So I'm going to give you a couple of minutes to read it, sort of absorb it, write down in your notes what you need to write down, and then I'm going to comment on it. So the first statement and the underlined statement are basically the same thing that the previous slide mentioned, or what I mentioned on the previous slide, that you have to have two objects and what we defined a force as, that there has to be two objects. But then the law, more officially stated in the red box, is maybe a more formal definition that if an object exerts a force on a second object, then that second object exerts a force that is equal and opposite in direction from the first. So it's not exactly what you often hear quoted as for every action, there's an equal and opposite reaction. That's not exactly Newton's third law, but it's related. For every force, there has to be an equal and opposite force. And there has to be a pair of objects, and forces come in pairs is another way to say this. We'll see that on the coming slide. The example you see here, we've got a cat laying on the table. So the two objects are the cat and the table. There has to be two objects. The two forces are the cat has weight. Everything that is made up of matter has weight, even air, gases, they all have weight. It may not be a lot, but they all have weight. Every type of matter has weight. So this cat has weight, and that weight is generated because of the gravitational force field of the Earth. So all matter has mass, and as long as there's gravity, there's going to be weight, and there's nowhere in the universe where gravity is non-existent, at least not that we're aware of. So the cat, based on its mass and the gravitational force field of the Earth, has a certain amount of weight that it is pushing down on the table with. However, apparently it's not heavy enough to break the table, so the table is pushing back against the cat to keep the cat suspended off the floor. Those have to be equal and opposite. They have to be opposite for the cat and the table not to move, and they have to be equal for the cat and the table not to move. If they were unequal, either the cat would fall or rise, or the table would fall or rise. Something would be moving, because if forces are not balanced, then there is going to be an acceleration. There's going to be a change in the movement of the objects. When forces are balanced, then everything's okay. Just things that are already at rest will stay at rest, and things that are already moving will stay moving. This cat's at rest. So the forces of the cat on the table and the table on the cat must be balanced. So the force pair exists between these two objects. And that is basically what Newton's third law helps us to understand. Anytime two objects are applying forces, those forces have to be equal and opposite. Now, sometimes that seems pretty clear. I think for the cat on the table, that's probably not hard to absorb. but other times it seems a little strange. So if you're driving down the road and a bug gets splattered on your windshield, the force your windshield applied to the bug is the same as the force the bug applied to your windshield. And that seems illogical. It seems unusual because, well, it didn't really do anything to your windshield except get it dirty, but it totally destroyed the bug. So how could they be the same amount of force? And there's a lot of things to discuss in that. There's the structural integrity of the window versus the bug. There's the mass of the window in your car versus the bug. There's all kinds of things to discuss, and we will discuss some of those things in the future. But for now, just understanding that Newton's law tells us that bug applied the same amount of force on your windshield as your windshield applied on the bug. The outcome was quite different, but the forces were equal and opposite in direction. All right, let's move on from there and think about Newton's law, third law, a couple of other ways. Like we said, for every action, there's an equal opposite reaction. That's a way you may have heard it. But a phrase that I want to make sure kind of sticks in your brain is that forces come in pairs. You can't have a single force. Now, we may only focus on the force in one direction, but technically forces come in pairs. And so we may only be concerned about the table's support force on that cat, but the cat's weight is applying a force on the table, whether we want to think about it or not. It exists. So forces always come in pairs. All right, any questions so far about Newton's third law? What it means? We've basically defined it now a couple of ways, but all right. Let's look at another example here. If we are applying Newton's third law, there has to be two objects. So if we have this person here either doing push-ups or a plank of some sort, if we're focusing on the hands of the person and the floor, that's our two objects, hands and floor. The hands are pushing down on the floor is pushing up on the hands. That's the force pair. There's two objects, hands and floor, and there's a very specific pair of forces that are equal and opposite. Now, this does not have anything to do with the person's head or shoulders or any other part of the body. It doesn't have anything to do with the earth or the air or anything. We're focusing in on two objects, the hands and the floor. And between the hands and the floor, there is an equal and opposite force pair. Okay, so when we're thinking about force pairs and Newton's third law, we have to be careful that we are really clear about what the two objects are. It would be a little too vague to say between the person and the floor, because the only part that we're really focusing in on is the person's hands. Okay, that's what we're focusing on. So we want to be pretty specific. And we don't want to say the floor and the earth. We want to say just the floor. The earth is something different. So we don't want to add a third thing in. If we're thinking about force pairs, we have to limit ourselves to two objects only, because there can be two and only two objects within that force pair. So we need to be pretty specific when we're thinking about Newton's third law. All right. If we add a third object, it's not that we can't do that and evaluate a system. We will, but we're no longer talking about Newton's third law anymore. Once we start adding a third object or a third force, then we're talking about a system, not just a force pair. And Newton's third law is specifically about force pairs. All right, another example of Newton's third law is propulsion. And so when you have a rocket launching or any other sort of propulsion system, that is a thrust force. It is a contact force. From your reading, hopefully that phrase contact force makes some sense. We'll touch on it a little bit later, but when the combustion in the engine burns those molecules get pushed off of the engine out of the back, and then therefore they are pushing on the engine in the other direction. And since the engine is attached to the rest of the rocket, all of the rocket gets propelled upwards by that equal and opposite force. And because there are billions of molecules being burned and thrust out of the back, applying a force against those molecules down, the force those molecules apply up against the rocket can propel the rocket upward and accelerate the rocket upward. There are some more videos here. Again, we're not going to show them in a Zoom session, but if you really like videos, if they're helpful for you to picture things and imagine things, these are 3 good ones. You'll also find those if you go to topics again, Unit 5A, Unit 5B, Unit 6, you'll find all kinds of videos. The ones I'm listing here, plus a bunch more. Some of them are like these, a little bit more entertainment slash, or maybe edutainment, education and entertainment focused, where they're just helping you visualize things and see things. And then some are very like problem solving focused. So you'll see a variety, lots of different things. It's partly also why I divided into 3 categories. The first 2 are more focused on balanced forces, when forces are balanced for the most part. And I divided into 2 parts before, in terms of before Thanksgiving and after Thanksgiving. And then the third one, Unit 6, is more focused on when they become unbalanced, and then we start working at angles and more advanced scenarios in that last part. So one of the videos, this Dr. Carlson video, is one where he actually sits on a skateboard with a fire extinguisher, and he's in this hallway at Purdue University, and he fires the fire extinguisher, kind of like the rocket propulsion scenario here, where the fire extinguisher is spewing molecules out of the fire extinguisher, but to apply the force on those molecules, the molecules have to be applying a force on the extinguisher, and since he's holding the extinguisher, it pushes him backwards down the hallway. So it's our weekly Monday interruption by the gardeners, if you can hear the blower in the background. So if you're curious and you'd like to see that in action, you can watch his video, or the TED Ed video and the Veritasium videos also have some interesting things to think about. The last one here to think about Newton's third law is to show you how we can represent those force pairs with subscripts. So we've used subscripts already in all of our kinematics, like final velocity, final position, initial position. We've sort of developed that habit already. But here I want you to see that when we use subscripts with forces, most of the time we will just put one subscript, like this is gravity, the force of gravity, or this is the normal force, or this is the friction force. Most of the time we'll just have one thing. But when we're thinking about Newton's third law, you may want to put 2 things, because it helps you clarify what are the 2 objects we're talking about here that create the Newton's third law pair. And so in this case, they're talking about this girl walking along the ground. And so they're abbreviating. The G is the ground force the ground is applying, and the P is the force the person's foot is applying. And so they're just showing you could use 2 subscripts to say, like, the force of the ground on the person's foot is equal to and opposite of the force the person's foot applies on the ground. And that's how we're able to walk. We apply a force on the ground, the force of the ground applies an equal and opposite force on us, and it propels us forward. You could also, instead of using the equals a negative in terms of the equals and opposite, you could also just use opposite pointing vector arrows to show that they are opposite, and then the equal sign between them to show that their magnitudes are equal. So you can use vector arrows to show that they're opposite, or you can make one positive and one negative to show that they're opposite, but yet their magnitudes are equal. And force is a vector, so it does have both magnitude and direction. It makes sense that it's a vector because when we learn Newton's second law, we're going to determine that force is calculated by multiplying the mass of the object times its acceleration. And acceleration is a vector, therefore the resulting force we would calculate is also a vector. So any questions on Newton's third law? All right. So back to the general introduction. We already had this statement on here that the force, a force, is an interaction actually between 2 objects and substances. We've further evaluated that and expanded that to clarify that means forces come in pairs. But some forces are what we call contact forces and some are non-contact forces. And I'm going to breeze through this pretty quickly because hopefully you did the reading and you understand this. There are 4 fundamental forces in nature. If you've had chemistry, you may have learned that 2 of the fundamental forces are the strong force and the weak force. They are nuclear in nature, and we're not going to consider them for our course. You talk a little bit more about them in AP Physics 2. So for those of you that might take that class, you learn a little bit more about those. And if you've had chemistry, you may have learned about them. In our course, we're going to limit our focus to the other two fundamental forces, gravity and electromagnetism. And the gravitational force and electromagnetic force are both non-contact, meaning they don't require contact to exist. If I'm touching the earth, there is a gravitational force. If I'm not touching the earth, there's still a gravitational force. We don't have to be touching. So gravitational force does not require contact. And when we talk about gravitational mass, we're really talking about how the mass is impacted by gravity. And the word we want to start using is the word weight. Weight is actually a force. Sometimes we'll just call it the gravitational force, but I prefer to just call it weight when we mean weight, and gravitational force when we mean the gravitational force between two objects. They're technically the same thing, but I kind of, in my brain, appreciate a little distinction in terms of the application. For electromagnetic force, if you've ever held two magnets close together, you know that there's an attraction or a repulsion before they touch. So if they're touching, it's still there. So it doesn't mean they can't touch. It just means it doesn't require contact. So those are examples of non-contact forces, forces that do not require contact. Now, there are a lot of other forces that do require contact. Two of them that we'll talk about today are friction force and drag force. And a lot of books actually just say drag is just air friction. So you could call all of these friction, but most books make a distinction to say that drag is the force that solids experience when they move through a fluid. It might be through air, which is air resistance, or it might be through water, which would be a different kind of drag. But remember, if you've had chemistry, hopefully you understand fluids are not all liquids. Fluid means the matter flows, which would include liquids and gases. So drag would just be when there's a solid that's being restricted in its movement because of its flow through a liquid or a gas. Friction then is the term we usually use when we're talking about solid to solid contact. And if those two solids are sliding over one another, there's actual movement between the surfaces, then we're talking about kinetic friction. If there's not a sliding of the surfaces, if the surfaces don't move it relative to one another, then that is considered static friction. So if I'm sliding a table across the floor and it's actually in movement and the surface of the table is, the legs are touching the floor and they're moving, that's kinetic. If I push on the table and it doesn't move, the friction that's resisting my push and keeping it from moving is what we call static friction. So it can get a little tricky when we talk about movement. For instance, that girl walking on the ground, static friction is what allows her to propel herself forward. If her feet slid, she wouldn't move anywhere, and that would be kinetic friction. But because they don't slide, they grip, it's static friction. So sometimes it's a little tricky. Same thing with a car. The car's grip on the road is static friction. Even though the car itself is moving, if the wheels didn't grip the road and stick, then they would be sliding. So if the wheels were spinning and the car was going nowhere, that would be kinetic friction. But if the wheels are propelling forward because of their grip on the road, that's static friction. So when we talk about that relative motion, we're talking about the surfaces. Are they literally sliding one across the other, like locked tires that are sliding across ice? Or is there contact that's either propelling to cause motion or resisting motion? So static friction can both cause and restrict motion. Kinetic friction means there has to be motion between the surfaces. And then we evaluate how much that friction impacts the movement based on a number called the coefficient of friction. And that number has to be experimentally derived, or you can look it up often between common materials. So if you wanted to find the coefficient of friction between rubber tires and asphalt road, you could just look that up. If you wanted to find the coefficient of friction between steel hockey blades and ice, you could just look that up. If you wanted to find the coefficient of friction between wood and wood, you can look that up. Now, depending on the type of wood, you might have to determine it experimentally because maybe you've got different surfaces of the wood. But every set of surfaces has its own coefficient of friction. And if they're common, you can actually look them up. If they're not common, then you have to experimentally derive them. And that's one of the experiments I'm kind of leaning towards doing Wednesday, is having you actually determine a coefficient of friction using an old school method and a technology driven method. I'm just not sure we have enough time in an hour and a half, but I'm thinking about that one pretty strongly. So we'll come back to the friction and coefficient of friction and those things in much more detail later. But in case I do that one on Wednesday, I wanted at least to get some knowledge of what those words mean from the reading and then from our discussion today into your brains. Some other contact forces are the normal force and buoyant forces. Now, buoyancy is something you talk again more about in AP Physics 2, so I'll only talk about what it means in this class. Normal force is something we will discuss frequently between now and Christmas and even after. Both, though, are existing contact forces because they require contact to even exist. Buoyancy is when there is a solid that's interacting with a fluid and floating to some degree. It doesn't have to literally be floating on the surface. It could be not floating, but still have less weight because of its buoyancy. So some people, you know, when they get into the water, they float really nicely. There's a few different reasons, but you might have full lungs, you might have higher body fat content. There's a lot of things, but depending on your overall density, you might float well. If you blow out all your air and you don't have a super high amount of body fat content, you might sink pretty well. But that doesn't mean there's no buoyancy just because you're sinking. You would sink in the water much slower than you would fall in air, right? So there's still a greater buoyancy on you. So buoyancy are those forces that exist between a solid and a fluid like water or air. That's pretty much all we'll talk about for today. And then normal force is one that we will dig into a lot. In math class, you may have learned that the word normal means perpendicular. And this is one of those cases where math and physics mean the same thing. You know, in an example we've talked about before with math, your teachers are always saying, leave the radical, don't turn into a decimal, leave the fraction. And in physics, we're saying, don't use fractions, don't use radicals, we need sig figs. And so because we have different purposes, we have different goals, we use math in a different way sometimes. But in this case, it's the same thing. The normal force is always perpendicular to the surface, just like the normal is always perpendicular in math. And the normal force is like that cat laying on the table. The table is applying what we call a normal force to the cat to support it. And it's perpendicular. It's just vertically upward for the cat's vertical downward weight. All right, so those are a couple contact forces you hopefully read about. Tension force is another contact force. It's like what you experience in a rope or a cable or a string or a chain, or even your muscles. There could be a stretching tension in your muscles if you're pulling on something. It is more solid to solid, and the stretching of the material might be visible if it's a bungee cord, or it might be not visible if it's a metal chain. It's microscopic where it's virtually unrecognizable. That there is any stretching, but tension force is another force we'll talk about, and another force that is contact based. All right, now here is a list of a variety of forces. This might be one we're screenshotting. It's not from our textbook, it's from a different textbook, but it's a table I thought was nice and orderly. It lists a bunch of different kinds of forces that we will frequently refer to, and it lists their most common symbols, although you will see some slight variations from book to book. And it also talks about what they mean and what direction they act in, generally speaking. So kind of a nice summary of a lot of the different kinds of forces we'll talk about. Now, the ones we're going to focus on before Thanksgiving are friction, normal, and weight. So we'll spend most of our time before Thanksgiving focusing on those three: the friction force, the normal force, and weight force. The spring force, tension force, and thrust force, it's not that we won't talk about them at all between now and Thanksgiving, but they'll be less of a focus. Those will be more of a focus after Thanksgiving, especially spring force. All right, so just a quick overview, nothing to memorize, but just to help familiarize you with some of the forces we'll be talking about. Now, some common misconceptions. Thrust force, looks like it's a little slow opening up here, at least on my screen, so I'll wait a few more seconds, see if it pops up. keep getting these notices that my internet is a little slow. There we go. That was a long pause. I don't know if you guys have the same length of pause I did, but my computers are literally side by side and it took almost 30 seconds for it to show. Anyway, some common misconceptions or clarifications. Thrust force and other contact forces, because they require contact, they no longer exist once the object becomes a projectile. So with the rocket, once the engine is done expelling the thrust force fumes, it doesn't mean the rocket's going to stop moving. It's just going to stop accelerating. So if I throw a ball, I'm applying a force to it. I'm thrusting the ball in a forward direction. And yet, once the ball leaves my hand, I'm no longer applying a force to it, but that doesn't mean the ball stops. It just stops accelerating, at least due to the force I applied. There might be some other forces causing it to accelerate, but my force is no longer causing an acceleration because it required contact. So a lot of times people get in their brain, and this sort of overlaps here with this second bullet point. A lot of times people get in their brain that for an object to be in motion, there has to be a force acting on it. And that's not true. For an object to accelerate, there has to be a force acting on it. But objects can be moving and not have any net force acting on them. In fact, objects won't stop moving unless there is a net force acting on them. So once there's no contact, those contact forces are not causing acceleration anymore. And that, like I said, overlaps a little bit with this, this second bullet point. Force is needed to keep an object in motion is not true. So people a lot of times, again, they think that force is required to keep an object moving. Force is required to cause acceleration, not to keep an object in motion. And when we talk about Newton's first law, the law of inertia, we're going to recognize that objects in motion will stay in motion unless there is a force acting on them. So you don't need a force for an object to keep moving. You need a force for an object to accelerate. As we talk about Newton's first law in greater detail, we'll use the word inertia a lot. And inertia is almost synonymous with mass, which is a little bit confusing sometimes initially, but I think you'll get the idea as we keep talking about it. So when we say inertia, we're not talking about any force. We're really talking about the mass of the object. It's a property of the matter that we're referring to. So for instance, if Jack and I decide, hey, let's go play catch, and we throw a football back and forth, it's not too hard. I mean, the football's not a lot of mass. We can throw it back and forth pretty easy. It's not very hard for us to accelerate it in the other direction. When we're catching it, it's not too hard to accelerate it in the opposite direction to make it stop because it doesn't have a lot of mass. It doesn't have a lot of inertia. But if we said, hey, you know what? Let's challenge ourselves. Let's play catch with a bowling ball. That's a lot harder. Like it's gonna be harder for Jack and I to actually throw the ball. It's gonna take a lot more work on our part to do that. And to catch it, we're gonna have to apply a lot more force to stop it because it has more mass, it has more inertia. So when we talk about inertia, it's not the force itself, it's really the property of mass that it has. The more mass it has, the harder it will be to start and stop its motion. And then the last one, air does exert a force. We often say that we're ignoring it, but that doesn't mean it doesn't occur. Or it doesn't mean it doesn't exist. And in fact, we won't always ignore it. Even today, in at least one of the examples we're going to talk about, we won't ignore it. So we have almost always ignored it so far. And I would say 90% of the time we can. But there are certain scenarios where we can't. And we'll talk about one today. So when we say we're ignoring it, we're not saying it doesn't exist. We're just saying it's negligible. In fact, a good example of this is a lab that unfortunately you guys haven't had a chance to do. It's one we usually do in Unit 4, which we just finished, but it's not one you can really do remotely. And I'm hoping maybe we'll do it at the end of the school year after the exam, because it's one that almost every year students say it was their favorite lab of the year. But basically, we go outside with Nerf guns and we shoot the Nerf guns and gather a bunch of data. And you shoot the gun maybe 50, 60, 100 times and gather a whole bunch of data. What angle did you shoot it at? How far did it go? How long was it in the air? You gather a bunch of data. And from the data, you basically generate your own kinematics equations model for your Nerf gun. And then we have what we call test day. And we go out to the football field, or if it's windy, we go into the gym. And I set out a little metal pie pan and tell you, okay, you have to shoot it from 10 meters. Your group has to shoot it from 15 meters. Your group has to shoot it from 8 meters. And you have to hit the pan. And so based on the mathematical model you come up with, you have to figure out either what angle should we shoot it at, or how high should we shoot it from, or a combination of both, depending on how advanced the model is that your group comes up with. And we completely ignore air resistance, because those little Nerf bullets, as long as it's not windy, that's why we sometimes have to go into the gym. As long as it's not windy, those bullets cut through the air pretty well. And even ignoring air resistance, I have groups every year hit that pan spot on. So it's not that we're saying it doesn't exist. We're just saying that for a lot of things, it's pretty negligible. It makes such a small difference, it doesn't really matter. We can ignore it. So that's really what we're saying when we ignore air resistance. All right, that's the summary of a lot of the things hopefully you picked up on from your reading. And there's a lot more in the reading that I'm not going to spend time talking about. So if you haven't read it, please do go back and read it. All right, now let's dig into Newton's first law. We've talked about Newton's third. Let's go to first and second. The first law says, and you've probably all heard this, an object at rest remains at rest, an object in motion remains at motion unless acted upon by a net external force. So I'm going to let you put that into your notes and read what's underneath that and decide if you want to add anything to that into your notes, and just give you a couple minutes to do that. So while the definition in the box is standard, probably most of you have heard some form of it. Maybe many of you even have it kind of in your memory as knowledge. I actually prefer to think about it as the second sentence on the page, because I think it taps into kinematics better. It touches on something we've been learning all semester. So another way to think about it is that an object maintains its velocity. And remember, velocity is a vector. So that means it's maintaining both its speed, its magnitude, and its direction. And so it's going to maintain its velocity both in speed and direction unless there is a non-zero net force. In other words, unless there's some unbalanced force that is causing it to change. And so it could be that the velocity is zero, and it will stay at zero unless there's an unbalanced force acting on it. It could be that the velocity is 2 meters per second in the northern direction. It's going to stay at 2 meters per second in the northern direction unless an unbalanced force acts on it. It could be that it's 2 meters per second in the northern direction, and then it goes to 2 meters per second in the northeastern direction. And so we've only changed the direction, but that is an acceleration. So a force had to be applied to cause that change in velocity. Any change in velocity means a force was applied, because forces are related to acceleration. All right, the last statement here, just as sort of a side note, the fact that something is at rest and has a zero velocity is not some sort of special case. We don't treat it differently. We don't have to use a special formula or do anything unique with it. It's just one of the many velocities an object could have. So don't get confused and think, oh, if it's still, we have to do something special. No, it just has zero velocity. So that's all you have to understand. There's no new scenario to it. Sometimes students just think, oh, it's a special case, I have to do something unique, and you don't. All right, Newton's second law. So Newton's third law helps us understand, okay, forces require two objects and forces always come in pairs. Newton's first law tells us forces actually cause objects to change their motion. If the object is at rest, it'll stay in rest unless we apply a force. If an object's in motion, it'll stay in motion unless we apply a force. If it's moving north, it'll keep moving north unless we apply a force. Forces change the motion. So that's what Newton's first law is telling us. And it's impacted by the mass of the object or the inertia of the object. And so that also is part of Newton's first law. Newton's second law helps us figure out how forces, or like maybe not how in terms of the why, but mathematically, how much will a force affect it? So it gives us some grounds for applying some math. So kind of summarizing, an object doesn't change its velocity unless a force acts on it. That's basically Newton's first law. The how does an object respond to a force is what Newton's second law helps us figure out. Okay, so Newton's first law tells us an object won't change its velocity unless there's a force acting on it. Newton's second law tells us, okay, well, how will that object respond when we apply a force? All right, and anybody know the equation for Newton's second law that helps us mathematically evaluate it? It's a really short law, only 3 letters.
Equals MA.
Yeah, I saw Nat raise her hand too, but I think Kayla got it. F equals ma. And that equation, we're going to look at slightly different. We're going to add this little sigma symbol. For most of you, you've probably learned what that sigma symbol means in math class. It means literally to sum up or add up the forces. So you could call this the sum of all forces. But in physics, rather than calling it the sum of all forces, which is fine, it's not, you're not wrong to call it that, but it's much quicker to just say net force. And so it is the sum of all the forces. It's adding every force that's acting on an object up and finding out what the sum would be. But remember, it's a vector sum. So we can't just literally add the numbers. We have to add their number values, their magnitudes, and we have to consider their directions as well. So it's a vector sum. But if we sum up all these vector forces, we get a net, we get an answer. And so we more typically just refer to it as a net force. And if the net force is 0, that means all the forces are balanced or there are no forces. And very seldom are there no forces. It's usually just that the ones that are there are balanced. If the net force is not 0, then that means the object is going to accelerate. Depending on its mass, it may accelerate a lot or it may accelerate a little, but it will accelerate if there is a net force that is not 0. So that's why we use that little sigma. And sometimes you'll see the sigma, sometimes you won't. Sometimes you'll see it as F with a subscript net. And if you've learned the word net in more of an economics scenario, it means pretty much the same thing. If any of you have had a job where you've earned a paycheck, when you get your paycheck, it shows you, oh, you earned this much money. And then minus taxes, minus Social Security, minus all this stuff. And then here's how much you get. And that's your net pay, right? The net's what your take home is. So in forces, you've got all these forces, but some cancel out, some don't cancel out. And only the ones that don't cancel out are really the ones we need to concern ourselves with. And so those are the net, the leftovers. And so I think that's all. Anybody need more time on this slide? To me, the advantage of this is in terms of thinking about it as an equation is now we can mathematically figure out some things about a system of objects. But a question that College Board frequently asks is about proportionalities. So we're going to practice that a little bit. Let me just have you read this for a couple of minutes and jot down a few things into your notes, and then I'm going to ask you some questions. So if we rewrite Newton's second law as instead of F equals ma, if we write it as A equals F over m, we just use algebra to rewrite it and solve for A. It helps, I think, to think through the proportionalities better. Because the question that College Board often asks is to ask, how will the acceleration change if you do this to the force? Or how will the acceleration change if you do this to the mass? It's a very common question that they'll ask. I can guarantee you're going to see it on a quiz or a test about forces for me. And I can almost guarantee it'll show up in some way on the exam you take in May. So this is actually kind of an extension. This whole unit is an extension of what we've been doing with kinematics. Some of the things that we sort of took for granted in kinematics or learned through our PhET simulations, now we're going to actually start to understand the background of why. And this is part of that. So we're kind of digging deeper into this whole idea of why things move and change the movement. So acceleration is directly proportional to the net force. So if I double the net force, what happens to the acceleration?
It's increased.
If I double the force, how much does it increase?
Doubles.
Double. Good. If I cut the force in half, what happens to the acceleration?
It is cut in half.
Cut in half. Good. But acceleration is inversely proportional to the mass of the object. Its inertia is based on its mass. So based on the inertia or mass of the object, that's inversely proportional. So if I double the mass, what happens to the acceleration?
Cuts in half.
It cuts in half. If I cut the mass in half, what happens to the acceleration?
Doubles.
It gets doubled. Okay, so those are the kinds of questions that you'll be asked and be needing to think through. And if you rewrite Newton's second law this way, I think it's a lot easier to sort of mathematically quickly answer those kinds of questions. So, but that's what really Newton's law is helping us to do, is understand why things accelerate based on both the mass that they have and the force that's applied. So we're getting a lot of the reasons. We learned a lot of the what in the kinematics units, but now we're starting to learn a little bit more of the why. So units of force, this is the last bit about this Newton's second law. We've seen this equation multiple times. The SI unit, the International Systems Unit, is Newton, and we abbreviate it with a capital N. We can recognize, though, that literally, if force is equal to mass times acceleration, the SI unit for mass is kilograms, and the SI unit for acceleration is meters per second squared. So if we take kilograms times meters per second squared, nothing cancels. So the label or the unit for force is really kilogram meters per second squared. But because we use forces so much and we write them out so many times, we'll be writing out forces hundreds of times in the next few weeks. We don't want to keep writing kilogram meters per second squared over and over and over again. So we use the symbol Newton instead. But you do need to keep in mind what Newton stands for. So while it's easy to just write it, you need to remember that it really is kilogram meters per second squared, because when you're solving problems, that's the only way you can dimensionally check your units. So knowing that units of Newton's means kilogram meters per second squared is great. Writing it as Newtons is great, but you want to make sure you understand how to use it also to check your dimensions when you're solving problems. And we're going to be expanding on next semester. We're going to learn about joules, which is a Newton meter, which really means it's a kilogram meter squared per second squared. So we'll be expanding on these units as we go. So you have to keep that in the back of your mind. Any questions about Newton's laws? We've done a quick flyby and introduced them. We'll spiral back around to them again Thursday a bit, but. All right, let's apply Newton's second law here with a couple quick math questions. So you can just put your answers in the chat when you've had a chance to solve these two questions. First, what force is required to accelerate a 1,000 kilogram sports car at 6 meters per second squared? Go ahead and put your answer in the chat when you've got it. All right, good. We're recognizing just the simple use of Newton's second law, F equals ma, taking the mass of 1,000 kilograms times the acceleration of 6 meters per second squared, and recognizing that would be 6,000 newtons. And the last one to practice, a 12 Newton net force acts on a 36 kilogram object. How much does it accelerate? Got a couple answers starting to show up. All right, now they're starting to flood in a little bit faster. So if we're trying to find acceleration, that's force divided by mass, and 12 divided by 36 is 0.33. Now, just a quick reminder, this is one of those areas, like we said before, where physics and math butt heads a little bit. For physics, we need to know sig figs. So 12 newtons is 2 sig figs. 36 kilograms is 2 sig figs. So my answer can't be written as 1/3 meters per second squared, because 1/3 is exact. It does not show sig figs. I need to write it as 0.33 meters per second squared with those 2 sig figs. Okay, so just a quick, very quick sig fig reminder there. All right, the last topic of the day. We'll spend just a few minutes learning about free body diagrams. And free body diagrams are a way for us to represent forces at play on an object. So we're going to look at an example here. We've got a man pulling on a crate, and to the right, we see a free body diagram of the forces that are at play on the crate. So the first thing we want to do is to identify one object and represent that as a dot or a box. In this case, we're representing it as a dot. So you might remember our conversation back when we were drawing motion maps, and we said a bird's no longer a bird, the bird becomes a dot. A train no longer is a train, the train becomes a dot. So we're kind of using that same mentality here. We're thinking about the crate, but we're just going to draw it as a dot. But instead of mapping its motion, now we're going to map the forces that are affecting that object. And so if you see this F with a subscript G, that is the weight of the crate. It is how gravity is applying a force pulling the crate down to the center of the earth. Now, it doesn't actually go to the center of the earth, but that's the direction that it's being pulled. Because it doesn't go to the center of the earth, there must be some other force pushing in the opposite direction. And what do you think the N stands for based on what we learned in the reading and also in our lesson today?
Normal force.
Normal force, good. And that put FW equals mg into the notes. You can put FG or FW. Sometimes books even just do a capital W, which I don't like at all, because we're going to learn later capital W means work. And so I really don't like that, but a lot of books do it. I'll show it to you once or twice in our notes just so you've seen it before. But I strongly prefer F sub G or F sub W, or even F sub mg if you want. But it will be, the weight will be mg, and we're going to be learning that like Nat mentioned here. Now there's two other forces. Those two cancel each other. The normal force of the ground holding it up and the gravitational force of the Earth's gravitational force field pulling it down, they balance each other out so the crate does not rise or fall vertically. However, there is friction resisting the crate's movement, 200 newtons in the backward direction, and yet this person is accelerating the crate forward, so he must be pulling with a larger than 200 Newton force. Just based on the scale of our arrows here, if that is 200, maybe this is 700 or 800. We're just drawing it roughly to scale here to show the values. So that is an example of a free body diagram. There are certain steps you need to take, and I'll show you those steps now. I've talked them through in this example, but here is a sequence. If you like to have more of a step-by-step, if that's kind of how your brain works, you prefer to have a sequence. The first thing you need to do is pick the object that you are going to analyze or that you're being asked to analyze. So while forces come in pairs and there have to be two objects to create a force, when we draw a free body diagram, we're going to narrow our attention down to just one of them. So whatever force we're being asked about, we narrow our focus down to that one object. And we draw it as a dot, or we can draw it as a box. So on the previous example with the crate, I represented it as a dot. On the couple of examples we're going to look at after these steps, I have it drawn as a box, just to show you that both ways are fine. In class, I will almost always draw it as a dot. In most books, you'll see it drawn as a dot. Once you've picked your object and you've drawn your dot, then you're going to start using vector arrows to represent every force that you need to think about, every force that's acting on that object. And you need to make sure that you label it with some label. Now, there are some sort of acceptable labels like F sub W or F sub G for weight, or F sub N for normal, or F sub F for friction. But sometimes it's not really one of those more broad terms, and it's something you just don't know what to call it. You could just call F push or F pull or F applied. So you can give it a very generic name. If it doesn't really seem to fit normal or gravity or friction or something, you could just call it pull, push, or applied force. And then you need to make sure that all the forces' tails start at the box or the point, like they did on that previous picture, and that their directions and their relative size tell you about the nature of the vector. They tell you something about the magnitude based on how long the arrow is, and they tell you the direction based on which way the arrow is pointing. So those are the things you need to do when you're drawing a free body diagram. Anybody need, put your hand up if you need more time on this slide. Okay, not seeing any hands raised, so we'll move on. Let's look at some examples. So the first example, we just have a book sitting on a table, not going anywhere, not doing anything. So thinking about the forces that are acting on the book is being pulled down by the earth, but the book is being lifted up by the table. So those are really the only two forces that are at play. And if we're focusing on the book, we need to draw a dot or a box to represent the book. And then we need to draw the arrows from that dot or box. So in this case, we know that there's an upward force and a downward force. They both have to originate from the dot or the box. So we would draw from the dot or box a downward arrow representing gravity and an upward arrow representing the normal force that the table supplies. We know that they have to be balanced because the book is not rising or falling. Since the book is staying stationary vertically, there is no net force. They balance each other out. The net force is 0. All right, questions? Okay, just a couple more to wrap it up. We're about done here. So now we've got an egg that got bumped out of the nest. As you know, we normally ignore air resistance. So an egg is relatively aerodynamic, so we'll ignore air resistance on this one. And that means that it is accelerating downward. Since it's accelerating downward and gravity only affects things vertically, we would draw the free body diagram for this one as just a single downward gravitational weight force, pulling it down, accelerating it downward. Since there is only one vertical force, there is a net. It's not 0 anymore because there's nothing pointing upward to balance it out. So this does have a net force, and therefore it will accelerate as it falls down. And we already know about free fall. We already know about projectile motion, so that hopefully makes sense. But now we're just thinking about it from a force perspective. Questions? All right, here's one where we do need to take in air resistance. This is not just your everyday squirrel. This is a flying squirrel. I don't know if you've ever seen these in real life or in videos. So, and these flying squirrels, they don't flap their arms and fly, but they have big flaps of skin between their legs, and they stretch their legs out, and it's almost like a built-in personal biological parachute. Okay, and so it's not that they fly really, they just float sort of. They reach terminal velocity. So if you've ever heard of that term, terminal velocity, squirrels, they don't have much mass, and they've got a lot of surface area to catch a lot of air. And so their air resistance actually, while they're falling, they'll reach a pretty small terminal velocity like a parachute does for a skydiver. And so they'll accelerate for a little bit because of gravity, and then they'll reach their terminal velocity and they won't speed up beyond that. And so they get a gentler landing as they hit the ground instead of like we would without a parachute. And same thing for skydivers with a parachute. So in this case, we have to think about air resistance because air resistance is what allows them to quote unquote fly. So if they have reached terminal velocity, if they actually have their skin flaps all catching the air and they've reached their maximum falling velocity, then the air resistance that's holding them up a bit is balanced with gravity's force pulling them down. It doesn't mean they stop falling. Just like a skydiver. Skydivers don't stop falling when they reach terminal velocity. They just stop accelerating. So when you jump out of an airplane and you open your parachute, you don't quit falling. You just quit accelerating at some point. All right. You reach your terminal velocity, the fastest velocity that you can reach with that given air resistance. So when you have a large surface area, you can create air resistance to reach a better terminal velocity. Things like golf balls and arrows and stuff, their terminal velocities are hard to reach because they have such aerodynamics. They don't really gather a lot of air resistance. So, but other things do. So that would be the free body diagram for a flying squirrel that's reached terminal velocity. All right, got two more to wrap it up. A rightward force is applied to a book at rest in order to move it across a desk. Consider friction force, because that wouldn't really be negligible. We would actually feel the friction. But we could neglect air resistance in this one. I wouldn't really feel the air pushing back on me while I'm pushing this book across the table, but I would feel the friction. All right, so if I barely push it with my pinky, it might not move, but if I push it a little harder, I can overcome friction and actually get it to go from being at rest to actually moving. So how many forces are acting on this book?
4.
4. What are the 4 forces acting on the book? Nat?
Friction, push, gravity, normal.
Yeah, friction and push would be horizontal. Gravity and normal would be vertical. Which ones are balanced?
Gravity and normal.
Yeah, because the book is not going to fly up or fall down. It's not going to change its position or its movement vertically. But would the horizontal push and friction be balanced in this scenario?
No,
How do you know that, Nat?
because it said it's moving rightward. So that means it's moving in a certain direction, meaning that the force cannot be equal.
Yeah, you're almost there. There's one little detail we have to add, because it's possible in a different scenario that something could be moving and not accelerating. And so there wouldn't be a net force. They would be balanced. But there's one key thing to add to what you said that makes it for sure an acceleration in this case.
It started at rest, so it has to accelerate to go faster than 0.
Right. So the fact that this started at rest, it had a 0 velocity. Now it's moving, so it has a non-zero velocity. That means the velocity changed. If the velocity changed, there's an acceleration. If there's an acceleration, there is a net force. So it's like the chain of what we've been learning to now what we are learning, right? So if we draw this free body diagram, we've got normal force and gravitational force balanced, equal and opposite, because the book is no longer rising or falling. But the friction is resisting the movement. However, the applied force is greater. So there is a net force in the horizontal plane, which allows the book to go from being at rest with a 0 velocity to actually having some velocity. All right, last one. A punter has kicked the ball. The ball is in the air, And we'll say that the ball is reasonably aerodynamic enough that the air resistance is pretty negligible, not a very windy day. So what would the free body diagram look like for the ball now that it's in the air? Got an idea,
On
Ethan?
the kick, or now that it's like exactly in the air?
Now that it's in the air. So Ethan, you had an idea?
It'd just be gravity, right?
How's that possible if it's moving side to side?
Because it's not accelerating side to side. So it's
Yes,
just
excellent.
inertia.
Excellent. So Nat's question is related to that. So it had to have a force initially from the foot to make it go side to side, but now that it's in the air, that foot's no longer touching it. And that force is a contact force. So that foot contact is no longer existing. So there is no horizontal force. It's not accelerating horizontally. It is only being accelerated by gravity. All right. That is good for today. We're almost out of time anyway. We've covered a lot of ground. Reminders, your assignment tonight, go back to Axis, open up topics 5A or unit 5A under topics and read readings 2 and 3. If you haven't read 1, if you forgot, do that too. So you should have, by the time we meet Thursday, have read readings 1, 2, and 3. No written assignment, but if you have time and you want to start working on the positive physics, go ahead and start working on positive physics. On Thursday in class, we'll probably take 20 or 30 minutes to go over the Unit 4 test and do some corrections in class. But if you want to get a head start and want to start working on your corrections now, you can go ahead and begin that. The same process as normal. You should do your corrections on a separate sheet of paper, all the same guidelines we've normally had. It needs to just be done by next Monday night. So you've got a full week to get it done. But if you want to get a head start, you can. So those are the things to keep in mind. And if you want to come Wednesday to Wellness Wednesday, don't forget to go to that announcement, click on the Google Doc link and add your name to the list. And that is all I have. If you have questions for me, stick around. Glad to chat. If not, you're dismissed for the day, and I hope you have a wonderful afternoon.
Thank you.
Thank you.
Thank you. See you.
See ya.
I have a question about number 1 on the Unit 4 test.
Okay.
I put a sine equals and then a cos equals, and then I put a sine 0, a cos 0. What's wrong about that?
So which choice did you pick? The first, second, third, or fourth?
I picked the first and it's the second.
You picked the, what do you mean this is second?
I picked the first one and the second one's the correct one.
Oh, no. So I think you misinterpreted the question. It's only one of these 4 pairs both works. So it's saying the components could be stated as this or that. And so you're trying to find the one pair that both are true.
Yeah, but how is the one that I picked, which is the sine 0 is first and then cos 0 is second.
Mhm.
And then the one that says it's correct is cos 0 and sine 0. How is
Okay,
there a
so-
difference?
Yeah, so if I'm looking at, when we write a coordinate pair, it's x, y. So if I'm trying to find the x, that's the adjacent side, so I need to use cosine. And then the opposite side would be the sine for the vertical, it's my y. So for the x and y components, it would be cosine for the x and sine for the y, based on that theta, that 0 looking symbol.
Oh, that's what it was. So it's like in order, like x, y.
Yes. Yeah.
Okay, that makes so much sense. I was just so confused.
Yeah, so the only one that works in both pairs is part B, or the second
Okay.
choice, I guess. It's B on my paper, but I think they weren't really labeled on yours.
Yeah, mine. Yeah, it's
Just
not
the
labeled.
second one there.
Mhm.
Yeah,
Okay, thank you.
you're welcome.